Hello world, and welcome back to an introduction to artificial intelligence. So last time we took a look at how AI can make predictions. We did things like predict the weather using AI, looking at problems like regression and classification as examples of types of problems that AI might try to solve. And ultimately, the way we solved those problems was through data. We gave our AI access to some data. It used that as training data. And based on the training data, it was able to learn some general patterns so that AI could make good predictions. Today, we're going to continue that exploration, looking at how AI can analyze data to solve other kinds of problems as well. So data takes a lot of different shapes. It can come in a lot of different forms. And let's think about what form the data took when we looked at it in the context of something like regression or classification. In those cases, for example, if we were trying to predict if the day was going to be raining or not raining, for each day, for each point of data that we had a whole bunch of information about that day, information like the temperature, the air pressure, cloud cover, and humidity. And then at the end, we had something we were trying to predict, like is it going to rain, yes or no. And we had not just one data point, but a whole bunch of data points, examples of pieces of data of all of these different forms. Now, these individual pieces of information, the inputs to our prediction problem, like temperature, air pressure, cloud cover, and humidity, those are what we called the features of our data set. We're using the features to try to make a prediction. And the thing we're trying to predict, we generally call the label. We're labeling each one of these data points with either yes, raining, or no, not raining, for example. Or alternatively, you might use a number. We might use 1 for yes and 0 for no. But that label is the thing that we're trying to predict. And anytime we set up an AI problem in this way, where we have a bunch of data, we have a bunch of features, and we're trying to use those features to make a prediction, we call that supervised learning. Supervised learning in the sense that the label is directing the AI, telling it what to try to achieve. It's trying to do a good job of predicting that label. But data comes in a bunch of kinds of forms. Data doesn't always have a label. And so when we have data without a label, that's a different kind of learning that we generally call unsupervised learning. So in unsupervised learning, our data set no longer has this label at the end, this like rain, yes or no, and we're just left with some raw data. And yet still, we'd like AI to be able to do something useful with this data, to be able to solve some problems by looking at that data, coming up with interesting conclusions, and doing something valuable with the result. So that's what we're going to be exploring today, looking at how AI can analyze data sets and come up with useful solutions to problems that we might have based on that data. And we'll look at a couple of different kinds of problems. And the first one we'll take a look at is the problem of clustering. So what are we talking about when we're talking about clustering? Well, we might imagine having a bunch of different pieces of data of different forms, and that might take the real form of something like a book, for example. I've got some bookshelves here. I've got a book here. And ideally, I'd like to keep my books organized, right? Usually, I don't just have one book, but I might have many different books, for example. And I want to keep them organized, and I might want to organize them across different shelves, for example. But I have some choices as to how am I going to group these books together in some logical way. Like maybe I could just throw them onto the shelves and just randomly arrange them. But ideally, books that are related to each other in some way are going to be close to each other on the shelf. And I can make some decision about how I want to cluster together, or how do I want to group books together. So anytime we're taking data and we're trying to figure out how are we going to group that data into different categories where we don't know in advance what those categories might be, but we're just trying to come up with groups of related items, we call that clustering. So in this case, what we're trying to do is we're trying to take our books and divide up those books into individual clusters. And you might imagine, how would you organize books? There are different choices for how you could do that. Maybe I could organize books based on the genre, what kind of book it is, where fantasy books go on one shelf and mystery books on another and romance on a different shelf. Or alternatively, maybe I organize books based on when they were published. Books from the 1800s could go in one place, and the 1900s and the 2000s. Or maybe I'm going to group books by their author or by the title, the first letter of the author or title, for example, where different letters of the alphabet get grouped in different ways. So there are lots of different ways to do this kind of clustering. But what we're interested in now is figuring out, could a computer do that for us? Could we give a whole bunch of data to a computer and have the computer figure out what clusters should be, what objects are related to other objects, and take care of that clustering process for us, so we end up with a more organized form of that data as a result? So that's what we'll be looking at now, is approaches we can take to have a computer do this kind of clustering. And when might that be useful? Well, it has applications like your Photos app on your phone, for example. You might have taken a bunch of different photos, and yet maybe your phone's able to cluster those photos, group them into related memories from a particular event or a particular trip, for example, or it's able to infer based on what's in the photo, when the photo was taken, who's in the photo, where the photo was taken. It can use that information to figure out how you might go about doing that kind of clustering. Or maybe your music streaming app takes a whole bunch of songs that it thinks you might like, and it tries to cluster them together into related playlists, where maybe you have one playlist that's really good for when you want to focus, and one playlist that's really good for a workout. And it might figure out, based on all of these songs, how should I group them together so that related songs are in similar clusters to each other. Or maybe facial recognition technology on your phone can take a whole bunch of images of different people, of your friends and your family, and automatically cluster them based on the faces that appear in them, so that every photo of a sibling or a parent or a friend shows up together, clustered together inside of one group. So these are all examples of how we might use AI to do this kind of clustering. And importantly, the difference between this kind of clustering and a classification problem like we saw last time is that the computer doesn't know in advance necessarily what these clusters are. It doesn't know who all your friends and family are in advance. It's just going to take all the photos you have and try and figure out on its own what the clusters should be and how it should try to organize that kind of data. So let's take a look at an example and see if we can figure out how a computer might go about this clustering process. So I'll go ahead and show you a whole bunch of data represented visually here. And I might pose the question to you, like how many clusters do you think are in this image if each individual circle represents, say, a data point? And if I look at this image, I think I see like 3 clusters. Maybe you see fewer, maybe you see more. But here are the clusters that I see. I see that there's a definite cluster down here, these red points that all seem to be kind of close together inside of a group. And then I see another cluster over here, these points that I've colored yellow. They all seem to be pretty close to each other too. And then I see a third cluster up at the top, all these individual blue points as well. And so hopefully you intuitively, by looking at this data, can get a sense for, yeah, points that are close together, they deserve to be in a cluster together. But now what we'd like to do is come up with an algorithm that we could give to a computer. So we could have AI figure out what those clusters are without us needing to tell AI exactly, here's this one cluster here, and there's another cluster there. So how could we do that? Well, AI might have a hard time figuring out exactly where the clusters should be right away. But one strategy we've seen come up a few times in this course now is that we can start with an AI that's not good at something, and then over time improve it. We saw that when we had the AI playing that snake game where it started out not very good at playing the game, and over time it got better. We saw that last time in the context of neural networks, where the neural network started out not very good at solving the problem, but over time, by giving it access to more and more data, by training it, we were able to make the neural network better and better, iteration after iteration. And so why don't we try doing something similar here? AI immediately might not know where all of the 3 clusters are, but let's have the AI start with 3 bad clusters and try and improve it iteratively over time. So I'm going to go ahead and label what we call 3 different cluster centroids. And what a centroid is essentially going to be a representation of where I think the middle of the cluster might be. And so here are my 3 cluster centroids. And again, I just randomly pick these locations. The AI might randomly pick 3 spots to place these initial cluster centroids. This might not actually be where the clusters should be defined, but it's at least an initial starting point. And then what we'll do is we'll take each of the data points and assign it to one of these clusters, either to the red cluster, or to the yellow cluster, or to the blue cluster. And the way we'll do that is based on distance. Whichever cluster centroid a data point is closest to, that's the cluster that we'll assign it to. So for example, this point right here, its closest cluster centroid is this red one here. So this data point we would put in the red cluster, for example. So if we do that for all of the data points, we end up with something like this, where all of these points that I've highlighted here, their closest cluster centroid is the red one. So all of these, they are our red cluster right now. And then we also have our yellow cluster down here at the bottom. These are all of the points for whom that yellow cluster centroid is the nearest one. And then finally, we have this blue cluster over on the right. So this is a clustering, right? This is a way of dividing up the points into red and yellow and blue. And the red points are kind of close to each other, and the yellow and blue points are kind of close to each other too. But it's probably not the cluster that we came up with when we were looking at this intuitively and trying to get a sense for where do we think the clusters belong. Like, it doesn't seem like this point way down here really belongs in the same cluster as this point way up there. So ideally, we'd like to improve upon this. How can we improve upon this? Well, one thing you might notice is that these cluster centroids, so to speak, which we're supposed to represent like the middle of our cluster, they're not really at the middle of the cluster right now. Like here's our blue cluster, but this blue cluster centroid is way off to the side, for example. So let's go ahead and move each cluster centroid, the red, yellow, and blue centroids, to the average position of all of the points in that cluster. So it really is at like the middle of all of the points. So if I do that, if I move all of the cluster centroids to the middle. Sure. Hello world, and welcome back to an introduction to artificial intelligence. So last time we looked at how we can use AI to make predictions. We were predicting how much plants might grow, or trying to predict the weather, for example, solving other problems that were regression or classification, trying to either predict a number or predict a category. And ultimately, the way AI achieved that was through the use of data. We gave the AI some training data. The AI studied that training data and was able to understand something about the relationship between variables in that data to be able to then make some useful predictions. And that's where we'll pick up today as well. We'll be looking at how we can use AI to analyze data, analyzing data in order to draw useful conclusions and solve problems that are helpful to us. So data comes in many different kinds of forms. We'll take a look at one example that we saw last time, for instance, when we were trying to predict whether or not it was going to rain. We had individual data points where each data point represented one day. And for each day, we had data like the temperature for that day, and the air pressure, and the cloud cover, and the humidity. And at the end, what we were trying to predict is is it going to rain, yes or no? And we had that not just for a single day, but we had a data set of training data where it wasn't just one day, but it was multiple days worth of information. And all of the information we were using to make the prediction, like the temperature, the air pressure, the cloud cover, the humidity, those are all things that we call the features of our data. These are the pieces of information that we're using to try and make a prediction. And the thing that we're trying to predict is then called a label. The label is like, is it going to rain, yes or no? That is the outcome we're trying to predict. And we might call it yes or no, or maybe we convert it to a number and say 1 for yes and 0 for no, for example. But this then is what the data set from last time looked like. We had features. We were trying to use those features to predict a label. And we have problems of this form. This is what we call supervised learning. Supervised learning is a kind of machine learning where the idea is that we use features to try and predict a label. The label guides or supervises the learning process, so the AI knows what it is that it's trying to predict. But data doesn't always look like that. Sometimes we end up with data that doesn't have a label. And in that case, we call it unsupervised learning. So unsupervised learning would be if we had a data set and it didn't have this final column, this thing we were trying to predict specifically, and we just had some raw data. And yet still with that raw data, we want to be able to give it to the AI, and we want the AI to be able to use that information to be able to solve useful problems. So that's what today is going to be about. It's going to be about how can we get AI to analyze data, even if it doesn't have a label that we're trying to predict, and yet still solve some useful problems as a result. And there are a number of different kinds of problems that we might try to solve in this way. But the one we'll start with is the problem of clustering. And the idea behind clustering is we have a whole bunch of items, and we want to group them into different clusters, so to speak. So for example, over here, I have a whole bunch of books. So here's an example of a book. And odds are I don't just have one book. I might have many books in my home or in my apartment. So here are a whole bunch of books that I might be trying to organize. And ideally, I'd like to organize them in some way. I might be trying to put them on bookshelves, for example. And there are different ways that I could choose to take books and put them on bookshelves. I could, of course, just throw them on the bookshelf randomly, where they're in no particular order. But then it would be kind of difficult for me to find a book and make use of this bookshelf later. So ideally, I want to group or cluster these books in some way, where maybe each one of my shelves represents some kind of cluster. And there's not necessarily one right way of doing this. Different people are going to organize books on their bookshelves differently. For example, I have a few different options for how I could do this. So maybe I could choose to organize books by genre, for example, where all the fantasy books go on one shelf, and all the mystery books on another shelf, and romance books on a third shelf. But you might choose to organize your bookshelves differently too. Like maybe you choose, you know what, I want to organize a bookshelf by when the books were published. So all the books from the 1800s go on one shelf, and all the books from the 1900s go on another shelf, and the books from the 2000s go on a different shelf too. Or maybe you want to organize your bookshelf alphabetically, where books with a similar first letter, or where the author has a similar first letter, are grouped together, like A through H and I through Q on a different shelf. So there are a number of different options that we have for how to go about doing that clustering. And what our goal today is seeing if we can get the AI, get a computer, to come up with a way of clustering the data for us so that we don't have to decide exactly what object belongs in which cluster. We can give AI an algorithm that it can use to figure out the clusters on its own. So why might we be interested in doing that? Well, there are a number of different applications. You might imagine the Photos app on your phone, for example. You take a whole bunch of photos, and your phone might be able to automatically cluster them, automatically group them based on what memory they correspond to. Maybe you have a whole bunch of photos that correspond to a particular event or to a particular trip, for example. And your phone, based on information about the photos, like who's in them, when they were taken, where they were taken, for example, might be able to group them into individual clusters that are useful to you. Meanwhile, maybe the streaming music app on your phone is able to take a whole bunch of music that you might like and cluster them into different playlists for you so that similar songs are grouped together into a similar playlist. Like music that's really good for when you need to study and focus, maybe go in one playlist. And music that's really good for getting you energized when you're out on a workout, maybe those go into a separate playlist too. Or maybe your phone has facial recognition technology where you can take a whole bunch of photos of people's faces, of friends and family members, for example, and your phone can automatically cluster them based on the faces that appear in them. So all the face photos of a particular family member or friend of yours appear together in an individual cluster. And what makes this kind of clustering different from classification, which we talked about last time when we were trying to take a data point and say that, oh, today's a rainy day or a not rainy day, is that in the world of clustering, the AI doesn't know in advance exactly what the clusters are going to be. Like the AI doesn't know in advance all the names of your friends and family. It's just taking all of these photos and then trying to figure out how are we going to group them together so that similar faces show up in similar clusters or similar pieces of music show up in similar clusters too. So this then is going to be the goal, to come up with an algorithm to let AI do things like this so it can take data and figure out how to cluster that data together. So as we think about how an AI might go about doing that, let's go ahead and start with an example. And we'll start with a visual example. I've given you a whole bunch of data points that are shown visually here. And I might pose the question to you, like, how many clusters do you think there are in this image here? And if I look at this image, I think I see around 3 clusters. Maybe you see fewer, maybe you see more. But here are the clusters that I see. I see that there is a red cluster down here in the lower left of points that all seem to be close together to each other, that are in a similar region of this screen. And then I see a yellow cluster over here in the lower right. All those points kind of seem to be close to each other too. And then I see a blue cluster up at the top. All those seem to be a third cluster as well. And so hopefully when you look at this image, you can get a sense for, yeah, there seem to be around maybe 3 clusters here of points that are grouped together. But the question then is, how could a computer do the same thing? How could we give this data to an AI and have the AI come up with what the clusters really ought to be? And the approach we'll take here is an approach we've seen a couple of times now in the class, where we've started with AI coming up with a solution that isn't very good, and over time, we've made it better. And that's been a theme we've seen recur a few times now. We saw it in the context of game playing, where we had an AI that was learning to play that snake game. And it started out not very good at playing the snake game. It was crashing into walls a lot. But over time, it got better at the game through experience, through learning from reinforcement, for example. And then we saw a similar idea in the context of neural networks, where we saw neural networks that weren't very good at making predictions at first, but over time we were able to improve them by having them learn from their mistakes, learn every time and see how far away it was from the correct answer, and adjust the weights and biases of the neural network to make it more accurate in the future. We'll apply a similar idea here, where if it's going to be hard for us to come up with good clusters for AI to guess at immediately, maybe we can have the AI start with bad clusters and then iteratively improve it over time. So we'll go ahead and have the AI pick 3 cluster points to represent 3 clusters. And we'll do that randomly initially. So we'll just pick 3 random points. So we have a red point over here, a yellow one here, and a blue one here. And these are what we will call the cluster centroids. The cluster centroid here just means this represents kind of the middle of the cluster. It represents one of our, in this case, 3 clusters that we're trying to use to assign all of the points that are on screen here. And so how might we do this? Well, we now have 3 cluster centroids that, again, are totally random. What we had the AI do was just pick 3 random spots for these cluster centroids. And now we want to say for every point, we need to figure out what cluster does that data point belong to. And how are we going to do that? Well, we can do that by just looking at which cluster centroid is it nearest to. For any given point, whatever cluster centroid it's nearest to, that might make sense as a guess for what cluster it belongs to. So for this data point here, the closest cluster centroid is this red one here. So this point we'll say belongs to the red cluster. And so if we do that for all of the points, we end up with something like this. So all of these points that I've highlighted here, their nearest cluster centroid is this red one here. So they all belong to the red cluster. And then down below, we have all of these points here. Their nearest cluster centroid is this yellow one. So they all belong to that yellow cluster, at least for now. And then we have one more cluster over here. All the blue points, they form a third cluster. And technically, this is a way to cluster the data, right? All the red points are here, and the yellow points there, and the blue points over there. But it might not be a very good clustering, at least to your eye. It might look like something's a little off here. Like, it's kind of strange that this point down here is part of the red cluster, and this point way up here is part of the red cluster. Maybe those don't feel like they really should be part of the same cluster. So our initial clustering, maybe not so good. Maybe we'd like to improve it. So how could we improve it? Well, one thing we could say is these cluster centroids, remember, that's what I was calling them, they're not really at the center of their clusters right now. Like, if you look at this blue cluster centroid, it's way off to the right here, whereas all the blue points seem to be over here. So one thing we might do is say, let's take all of the cluster centroids and really move them to the center, to the middle of the points that form their cluster. And how will we know the middle? Well, we could take the points of all of the points in the same cluster and average them together to get the kind of average position of all of them. That'll kind of be the center. And so if we do that across all three of these examples, we can move the cluster centroids, and now they're kind of at the middle of their cluster. This red centroid is at the middle of the red cluster. The yellow one's at the middle of the yellow cluster. The blue one is at the middle of the blue cluster. So now that looks at least a little bit better, even though none of the clustering is still the same, at least. But now here's one thing you might notice. For some of the data points, they now seem to be in the wrong cluster, now that I've moved around where the centroids are. For example, for this point over here, it's currently in that yellow cluster, but actually it's closer to that red cluster centroid now. It wasn't before, but after we moved the centroids around, now this point is closer to that red cluster centroid. And so we might say this data point, it doesn't really belong in the yellow cluster anymore. It really belongs in the red cluster now, because that's the one that it's closest to. And in fact, that's true for a few different points. These three that I've highlighted here, these two, first of all, originally were part of the yellow cluster. But now both of these really seem closer to that red centroid. And meanwhile, this point over here, previously its closest centroid was this blue one, but actually now it's very slightly closer to that yellow one. And so as a result, I might reassign what cluster individual points belong to if now they're closer to a different centroid. And so I can say, all right, let's go ahead and change the color of them. Let's now make these part of the red cluster. We'll make that one part of the yellow cluster. And now I've updated how I've done this clustering. And now I can start to repeat this process. I'm iteratively trying to make the clusters better and better, one step at a time. I can now say these cluster centroids, they're no longer at the middle of all of their points anymore. So let's go ahead and move them again, move them to the middle of all of their points. And now say, are there any more that now appear to be in the wrong position? And well, yeah, now these two that previously were closest to blue, now they're actually closest to yellow. So we'll reassign those. And there is one up there that we're changing as well. And so over time, we're iteratively finding any points that now belong to the wrong cluster, that now have something else that is closer to them. These two were previously in red, but now they're actually closer to blue. This one now seems to be closer to yellow. And we'll update that again and again. And if we keep repeating this process, having AI do this over and over again, finding points that are in the wrong cluster and adjusting them, eventually, we'll end up at a point where we stop, where there's no more changes to make, where there's no more points that appear to be in the wrong cluster. And at that point, we can say that the algorithm is complete. And at that point, if we look at what we ended up with three pretty good-looking clusters. We have this cluster down here, which appears to be the red one, this cluster over here, this yellow one, and this one that was blue. And that kind of matches our intuition for what we thought these clusters should be. I'll go ahead and pause now. I'll get some water and then pick up from there. Your question is going to be answered. So this algorithm, where we started out with random cluster centroids and over time made them better by assigning every point to the cluster centroid it was nearest to, and then moving the cluster centroid so they were the average of the positions of all the points in the cluster, and then repeating that again and again, has a name. This algorithm is called k-means clustering. And it's called k-means clustering because what we had to do was pick some value of k, where k is the number of clusters that we wanted, in this case 3, and then we tried to cluster them together by ultimately repeating that iterative process of moving the centroids around and assigning the points to the correct cluster. Now, we did have to pick the value of k. We as the humans decided, you know what, let's start with 3 random points, and we went from there and tried to improve it over and over again. We could have picked a different value. Like, for example, imagine I picked 4 cluster centroids instead of 3. We can take a look at what might happen. Then instead of starting with 3 random points, we're going to start with 4 random points. And again, we'll assign each data point to whichever cluster centroid it's closest to. So if I do that, we end up with 4 different clusters in this case. I have a red one that seems to be there. Those are all the points that are closest to that red centroid. And then I have the blue one down here in the lower left. Those are the ones closest to the blue centroid. And then I have the green one over here. And then I have a 4th yellow cluster over there on the right. And again, we could repeat the same process of going ahead and moving the cluster centroids to the average position of all of the points in that cluster, and then reassigning any points that now appear to be in the wrong cluster. And we can watch what happens as we repeat that process again and again, looking for the points that are in the wrong place. In this case, it's just that one down there. And repeating the process, moving the cluster centroids. And if we do that a few times, we end up finding that we reach a steady state pretty quickly where there's no more room to go. At this point, all of the points seem to be in the correct clusters. There's nothing that's in the wrong place that we need to reassign. And we have 4 clusters. And it's kind of up to our judgment if we think, is that 4 clustering better than the 3 clustering we had before? Like, maybe this does deserve to be its own cluster. And there are algorithms that we could apply where we try and find the point at which adding more clusters doesn't seem to add nearly as much benefit as the previous clusters do. But this is one trade-off, and one choice we have to make when using this algorithm is that we need to decide how many clusters are we going to use. Now, in this case, I've been plotting the points we want to cluster in 2-dimensional space. You could imagine that each data point is really like 2 values, like an x1 value and an x2 value, for example. But in practice, often we have many more than 2 features, 2 numbers that we're using to represent any particular data point. So maybe if instead of having 2 features that I was using, if I had data where each piece of data had 10 features, the data might look something like this, where I have x1 and x2 and x3 all the way up to x10, for example. And while ordinarily a computer has no trouble dealing with that, like it's totally fine to have 10 different numbers that the computer is working with. Computers are capable of dealing with a really large number of values. When it comes time to trying to measure distances between them, we can run into some problems as we start dealing with objects in many, many dimensions with trying to figure out how far away things are from each other and trying to figure out what's close to each other. Because maybe we have 2 data points where for some of these values they're really close to each other, and for others of the values they're really far apart. And so often we run into at least some trouble when dealing with really high dimensional data, data that's got a lot of different values as part of it, like this. And so sometimes it's useful to be able to take high-dimensional data, a piece of data that has many features like this, and reduce it down to something smaller. Imagine taking like something 10-dimensional and reducing it down to, say, 3 dimensions, for example. And this is a problem that we call dimensionality reduction, where we have something that exists in many dimensions or more dimensions, and we want to reduce it down to fewer dimensions. So it's a little bit simpler. It's a little bit easier to work with. Maybe our algorithms will be able to deal with it a little bit more efficiently, deal with it a little bit better. And it turns out dimensionality reduction is not just a problem for AI. It's a problem that's come up in our own lives, too. For example, we could take the instance of sorry, let me back up. I'll repeat that. I'll go from, and it turns out it's not just a problem for AI. And it turns out dimensionality reduction is not just a problem for AI. It comes up in other contexts as well. For example, we could take the example of a globe, for instance. So I've got a globe over here. And this globe is a representation of the world. It's a representation of the world that exists in 3 dimensions. But the trouble is, if I want to represent the world on something flat, maybe I'm trying to represent it on a map that I keep in my car, or on my phone, or on my computer, where my computer is in a 2-dimensional world, well, this globe represents the world in 3 dimensions. dimensions, but ideally I'd like a two-dimensional representation of the world. And so what that might look like is I might have, say, a two-dimensional map, something like this. Here, too, is a representation of the world as well. It's just that one representation of the world is in 3 dimensions, and one representation is in 2 dimensions. And what I needed was some kind of algorithm, some process that can take the 3-dimensional world and project it or transform it into 2 dimensions. And when you take a map and you turn it into 2 dimensions, it's not entirely accurate. Some things get distorted a little bit. Some things aren't quite the right size or shape as they were in the real 3 dimensions. But hopefully at least does a pretty good job of capturing the patterns and the relationship between things. That the countries that were close together on my 3-dimensional globe, I want those countries to be also close together and ideally a similar shape on this 2-dimensional map as well. And so this is the kind of thing that we're going to ask our AI to be able to do, to be able to take something in a lot of dimensions, something like this globe, and turn it into something that has fewer dimensions so that it's a little bit easier for us to be able to work with inside of our algorithms. And so now we'll take a look at some algorithms that can do just that, take something in more dimensions and convert it into something that has fewer dimensions, for example. So let's give this a try. We'll go ahead and take some data that exists in 2 dimensions. We've got some x value and some y values, for example. And so I'll plot some data points here. And let's imagine that I want to take these 2-dimensional points of data and convert them into 1 dimension. Right now, they have both like an x value and a y value. They exist in this 2-dimensional space. I want them to exist in 1 dimension. And what does that mean? Well, 1 dimension is really just like a line. So what I'd like to do is just have a single line where all of my data points fall, so that ideally I can take my 2-dimensional world, turn it into something simpler, turn it into something 1-dimensional, while still preserving what's important about the data, that the data points that are close together in my 2-dimensional data should still be close together when I reduce it down to 1 dimension. And the data points that are like far away from each other in 2 dimensions, they should still be far away from each other in 1 dimension. So how could I do that? Well, I could try and project all of these points onto just this y-axis, going up and down, for example. Or go ahead and take all of these data points and really just take their y position. How far up and down are they? And here's what that would look like. I'm going to project all of those points onto this y-axis. And that's certainly a way to take my 2-dimensional data and turn it into 1 dimension. Now they're only along 1 line. But I've lost a lot of the information that was originally in that data. Originally, my data points were pretty spread out from each other. They looked pretty different from each other. Now they're all kind of bunched up. It's sort of hard to tell them apart. I've lost a lot of the information that was in my data to begin with. So while this is a way to project my 2-dimensional data onto 1 dimension, it's probably not the best way. A better way, for example, might be instead of projecting onto this y-axis, I could instead project onto the x-axis, the one going left and right, for instance. And so if we project all the data points down onto that x-axis, just looking at what their x value is, how far left or right are they, now we seem to be doing a better job. The points that were far away, like this point and that point, they're still far away in 1 dimension, just like they were far away in 2 dimensions too. So that's certainly one choice I could have made for how to take that 2-dimensional data, turn it into 1 dimension. And that worked OK for this data set. Let me give you a slightly different data set. Here's 4 more points. And imagine how might we try to project this 2-dimensional data into 1 dimension. Again, we could try seeing what happens if we project onto the y-axis. It'll look a little something like this. But again, we've lost a fair bit of information here, that these 2 points look pretty close to each other now. But originally, those 2 data points were actually pretty far away. So we might say, OK, let's try and project onto the x-axis instead now and see how that does. And well, if we do that, now these 2 points look pretty close together, whereas originally those 2 points were actually pretty far away as well. So we've lost a fair amount of information here there too. And no matter what choice we make, we're going to lose some information because we're going from more dimensions to fewer. But ideally, we want to minimize how much information we lose. We still want a pretty good way to represent the data and all of its complexity, just with fewer numbers than we had before. And so we don't just have to project onto a line going straight up and down or straight left and right. I could try and project all these data points onto this line here, just saying let's go ahead and find the closest position along that line. And if I project all the data points onto that line, now I think I've lost a little less information. It still looks pretty close to the original data, but now it still exists in just this 1 dimension. And so AI can use algorithms that do things like this to figure out what is the way to reduce the dimensionality of the data in a way that doesn't lose too much information. So we still preserve as much information as we can, but make the problem a little bit simpler, a little bit easier for our computer or AI to be able to work with. So that's one strategy we can use to try and make this clustering better. But there are other problems that we might run into when we're looking at clustering algorithms like k-means. Let me give you an example of another data set. Here's a data set that exists, again, in 2 dimensions. And I might ask you again, how many clusters do you think you see here? And if I look at this data set, I think I see like 2 clusters. It seems to me that they seem to be in 2 groups. But let's see what k-means clustering comes up with if I give it the number 2, k equals 2, and say, go ahead and find 2 clusters here. We're going to start with random points, a red cluster and a blue cluster. We'll assign all of the points to either red or blue, depending on which cluster centroid it's nearest to. And we'll repeat that iterative algorithm, trying to make our clustering better and better, one step at a time. We'll move the cluster centroids, reassign some points, move the cluster centroids again, reassign some points, and keep repeating this process a little bit more and a little bit more. And we're making a few slow changes over time. It's a gradual process. But if we keep doing this, eventually we'll arrive at a situation where hopefully we're not making too many more changes. And once we reach a position where we're not making any more changes, at this point we have our 2 clusters. It seems that we've essentially drawn a line through this data where the red cluster is on this side and the blue cluster is over here on that side. But odds are, even though this is what k-means clustering came up with, this is probably not the clustering that you saw when you were looking at this data to begin with. At least when I look at this data, what I see is I see 2 clusters as well, but I see like a cluster here in the middle and a cluster that's kind of a ring around that middle portion of the data. But k-means clustering wasn't able to find it, because when it's looking at just like the average position, it's not easy to say there's one cluster here and one cluster that goes around it, because the average position of both of them is kind of the middle of this entire data set. So we might need some other algorithms, some other approaches that we can use to try and do that kind of clustering that can deal with clusters that have a slightly different shape. And so I'll introduce one other algorithm we could use called db-scan, db for density-based scanning, looking for points of data that are very dense or very close together. And so here's what that might look like. So I have all of this data. And what db-scan will say is that if you take a point and you say, look at this point, and you notice that nearby it, for some definition of nearby, we the programmer get to pick what nearby means, like maybe some fixed distance. If it's got like a fair number of neighbors, and we can decide what that threshold is, if it's got a whole bunch of points that are near to it, well then not only could we say, OK, we'll make this part of a new cluster, we'll make it part of the red cluster, but all these points that are near to it, we'll make those part of the red cluster too. They'll all just kind of be part of that red cluster. And likewise, we could say, well, if this other red point, if in its near neighborhood vicinity, it's got a fair number of points for some threshold that we define, it's got a bunch of points that are nearby to it, we'll go ahead and make all of those part of the red cluster too. And we can keep repeating that process. Say basically for every red point, if it's got a whole bunch of neighbors, if it seems to be kind of a core point with a lot of data nearby it, anything nearby to it will make part of the same cluster. So for this point, anything nearby it will turn into a red cluster as well. And if you repeat that process across all the data, eventually you'll find this red cluster, this red ring that seems to go around all of the data. And then we're left with some other points that we can now analyze too. We could say, all right, for this point, it's also got a lot of points around it, but not any of the red ones. So we'll make this point a blue point, and then everything around it, that can be part of the blue cluster, for example. And repeat that. If we keep repeating that process, we'll end up finding a blue cluster that exists there. And so that's one way we could try and find a clustering like this. But it might also be the case when we use an algorithm like this, there will be some points that aren't part of any cluster. For example, we have this point over here, where if in its near neighborhood it's got like no points or very few, well, then maybe it doesn't belong in any cluster. Maybe it's some kind of an outlier or some kind of an anomaly. And that's something that AI can do as well, is be able to look for those kinds of anomalies, things that really don't belong with any of the existing data in our data set. I'll pause here and pick up from there. So this ends up being a useful problem for AI to solve too. Sometimes we want to give AI a whole bunch of data and have AI identify the anomalies, the things that don't really belong with any of the other pieces of data that are there, because that can be helpful in certain contexts. And this kind of problem we call anomaly detection, trying to find the anomalies in some data. And when is this kind of idea helpful? Well, maybe your banking application can look for unusual transactions. If it noticed you spent more money than you usually do, or in a location you don't normally spend it, or a time you're not normally spending money, maybe it could flag that kind of anomalous transaction to you to let you know that maybe there's some fraudulent activity going on in your account. Or maybe if you have a health app on your phone or your watch, for example, that app might notify you if it notices an anomalous heart rate or some other health condition that appears to be not normal, some piece of information that doesn't fit in with the rest of the data. It could alert you to that as something that you potentially want to look into. Or alternatively, if you're signing into an account on a website, for example, that website might be looking for unusual login attempts. If you log in from a browser you don't normally use, or from a location you're not normally signing into a website from, that might be flagged as an unusual sign-in, some kind of anomaly that it's detecting, so that AI can say, you know what, this might be something worth looking into. Maybe your password's been compromised in some way. Maybe you want to take action to try and secure your account. And so it can be quite helpful to have AI looking for anomalies, using strategies like that to find pieces of data that don't belong. So those are some of the things that we can do using AI, giving it some data, asking it to try and understand that data, in this case trying to find clusters and trying to find anomalies inside of that data. One other thing we might try to do is trying to understand the rules and relationships between some data set. And we call this association rules. And so we'll talk in a moment about what it looks like to look for these kinds of rules in practice. And I'll give you some examples. What do association rules look like? Well, association rules are all about taking data and understanding relationships between objects in that data set. So for example, maybe your phone suggests apps that you might want to open. Maybe based on your habits, you always open the weather app in the morning, or you always open the music app when you get in your car, for example. And so AI might try to understand the relationships between these pieces of information, understanding the relationship between, say, time of day and apps you open, or when you tend to open apps together, for example. And it might try to actually, I don't want to say it that way. Let me go back. Okay. OK, I'll go back from the end of the clustering example before association rules. Association rules. And then we're about to do the cut to the shopping cart demo, by the way. OK. So these are some of the problems that AI can solve if you give AI a whole bunch of data and ask it to analyze it. AI can look at that data, figure out the clusters that objects belong to, figure out where the anomalies or outliers in that data might be. But that's just some of what AI can do with data. There are other types of problems that we might try to solve too. And one such problem is what we call association rule learning. And what is association rule learning? Well, association rule learning is all about taking a data set where you have a whole bunch of items and trying to understand which items are associated with each other, which items are related to or connected to each other inside of that data set. And there are a number of ways that can be helpful. One example might be that your phone might often suggest applications for you to use based on your habits. That if it notices that every time in the morning after you turn off your alarm clock application, you then check the weather, for example, maybe it suggests the weather app as an app to use because it knows what apps you tend to use together, for example. Or maybe if you have a smart home, you might have routines where at particular times of day you often turn off all the lights or lock all the doors, and so it can understand relationships between your common patterns in your everyday routines. Or another example might be if you engage in online shopping. You're going and filling your shopping cart, buying some groceries online, for instance. We might have an application suggest ways to complete your cart. For example, if you're buying pasta, then maybe your shopping application is going to suggest to you tomato sauce and basil and Parmesan that you might want to buy, because it knows that pasta is often associated with those particular types of items as well. And so this kind of problem can be helpful because it allows AI to understand how different things are related to each other, how one item in a shopping basket might be related to some other item in a shopping basket too. And while we as humans might be able to look at that data and infer some relationships, as we end up with more and more data across more and more users, it can be harder for humans to find those patterns and useful for a computer to be able to find those patterns instead. So to give you an example of that, I have here an example of a shopping cart, and you might imagine that a website or a company that sells goods might have a whole bunch of data about different people's shopping carts and the objects that they happen to buy. And what we might be interested in doing is understanding the relationships and the patterns between those objects. And so that's what we'll explore next. And that's that, and then we'll cut to the demo. So I have here some items that you might find in a grocery store. And what we might be interested in now is collecting some data that AI can then analyze to understand the relationships between, say, shopper behavior at this grocery store. So what data are we going to collect? Well, the data we're going to keep track of is for each of our shoppers. We've got a shopper over here and a shopper over here. We'll keep track of what items they decided to purchase. So for one shopper, for example, maybe they decided to buy cheese, and they decided to buy some watermelon, and they decided to buy a lemon, and maybe they decided to buy an egg, and maybe they decided to buy a banana as well. And for another customer, maybe they got some butter, and they got a banana, and they got some milk, and they got a watermelon, and maybe they got an onion as well. And so we have a whole bunch of items now in different shopping bins. And now once we've collected a bunch of data, probably not just from 2 shoppers, but probably from many shoppers, the question we might then ask is, what can we learn from that data? What patterns can we identify based on the data of who chose to buy which particular items? And the simplest thing you might look for is like, what objects tended to be popular? If you know a lot of different people who shopped at our grocery store all bought bananas, well, that's useful information. We know that bananas are a frequent item, and so as a result of that, maybe we make sure we always have enough stock on bananas. Maybe occasionally we do a discount on bananas, for example, in order to take advantage of this information that we now know. But one thing we're interested in the context of association rule learning, is not just which items are popular, but which item sets are popular, collections of items that together tend to be popular inside of a data set. Where, for example, you might notice that popular in this case might be an item set that includes both bananas and watermelon, that in this case both of our shoppers chose to buy both of these items together. And it's not just that bananas themselves are popular and watermelon by itself is popular, but that this set of items tends to be bought together. And that can be useful information for our grocery store to know too, because we might care about knowing which objects to place near each other, what items should be near each other inside of the grocery store, or maybe what items to offer discounts on together. If you buy one, then you get a discount on the other, for example. So all of these are examples that we might want AI to be able to understand some patterns about and learn about. And you might reasonably ask, well, why do we need AI for this? It seems simple enough for me to look at my 2 shopping baskets and infer what the popular items are and what the popular sets are. But the reality is that as the number of shopping baskets grows, as we deal with not just 2 customers, but thousands, maybe millions of customers, and we start increasing the scale of the data, thinking about the number of different items that we're keeping track of, the number of possible item sets also grows pretty rapidly too, and it becomes difficult for us to efficiently calculate what the popular, what the frequent item sets really tend to be. And so here's where it's helpful to not consider all of them, but have AI use some algorithms that can help us understand this data, look at this data, analyze this data, so we can identify what the frequent item sets actually are. So that's what we'll take a look at next. We're just taking a look at the algorithms that computers can use to take all of this data, analyze it, and find those frequent item sets. And that's this demo. So I have here some items that you might find inside of a grocery store. So let's go ahead and collect some data that AI might be able to analyze and then work with. And what data exactly are we going to collect? Well, the data we'll be collecting is about each individual shopper, and we'll be keeping track of what items they choose to purchase. And that might be useful information for us to then use to decide how we want to lay out the grocery store and what kind of pricing and discounts we should offer, for example. So we'll go ahead and collect some data. So for this shopper over here, they might choose to buy some of these items. Maybe they choose to buy some of the cheese. Maybe they choose to buy a banana. Maybe they choose to buy some butter. Maybe they choose to buy watermelon. Maybe they choose to buy an egg, for example. And then we have a shopper over here who's also going to buy some items. Maybe they're going to buy this burger over here, and maybe they'll buy this tomato, and maybe they'll buy the watermelon, and maybe they'll buy the fish. We should do that again. I have here some items that you might find inside of a grocery store. And so now let's collect some data that AI might use in order to analyze that data and draw some useful conclusions. And what data are we going to collect about this grocery store? Well, the information we'll collect is about each individual shopper. So I have a shopper over here and their basket, and another shopper over here and their basket. And the data we'll collect is about which items each shopper chooses to buy. And we might use that information to understand what items are popular, how we want to lay out different items inside of a grocery store, and what kind of pricing and discounts we should offer, for example. So let's go ahead and collect some data. So for this one shopper over here, maybe they choose to buy some of the cheese. Maybe they choose to buy the banana. Maybe they'll buy the burger here. Maybe they'll get the milk, and maybe they'll get some watermelon as well. And then we'll have another shopper over here who will purchase some items too. Maybe they'll get the tomato, and maybe they'll get the banana, and maybe they'll get the fish, and maybe they'll get the watermelon, and maybe they'll get some butter as well. And so now we have two different shoppers that have purchased some items. And ideally, we have data not just on two shoppers, but many more shoppers than just that. But using that information now, we can start trying to analyze this data, trying to find patterns. And what kind of patterns could we analyze? Well, the simplest pattern we might try to look for is just like which items are popular, which happens to be popular inside of this grocery store. And in this case, we might notice that a whole bunch of shoppers, two in this case, have bought bananas, and so bananas might be popular. And that on its own might be some useful information. We could use that information to make sure we always have enough stock on bananas and use that to inform how we choose to price bananas, for example. But beyond that, what we might also be interested in is looking not just for frequent items, but frequent item sets, where an item set is a collection of items that are bought together. And so if we look at my two pieces of data here, I notice that in this case, this shopper has bought both watermelon and a banana. And this shopper over here has also bought watermelon and a banana. So it seems like this item set, the combination of bananas and watermelon, maybe they're popular together. It's not just that bananas on their own are popular and watermelon on their own are popular, but together, this item set of two different items together seems to show up in at least two different shoppers' baskets, at least for now. And I'm doing this with just two baskets, but of course, in reality, I might have much more data than just that. And it might be useful to identify what the frequent item sets are. Because if I know which items tend to be bought together, well, then in my grocery store, I can try and make sure those items are near to each other so it's easy to get both. Or I can use that to inform how I price and discount one, maybe where if you buy one thing, you can get a discount on the other, for example. And I can make those decisions by knowing some information about my data. And in this case, it was pretty easy for me to be able to tell this. I didn't need AI to be able to look at these two shopping baskets and say, oh, I noticed that bananas and watermelon together are popular. But as the data grows in scale, it becomes harder for us to do that analysis and easier for us to provide an algorithm that allows a computer using AI to be able to try and figure out this kind of thing on its own too. So as we have not just two shoppers, but many shoppers, not just the limited items that you see here, but many items that you might find in a grocery store, the number of possible item sets starts to increase rather quickly, especially as we look not just at sets of 2 items, but maybe sets of 3 or 4 or 5 or even more items that might be bought together. And it can be helpful to have some kind of algorithm that can look at this data and figure out what the frequent item sets actually are. So now let's take a look at an example at how AI could analyze similar kinds of data to try and identify those frequent item sets. So in this case, we'll have not just one shopping basket, but let's say 5 different shopping baskets, each of which has a number of different items. I've given each item in the store a number, for example. So this shopper has purchased items number 1, 2, 3, and 4. And the other shoppers have also purchased some items as well. And so what we might be interested in doing is measuring how frequently a set of items appears inside of this data set. And we call that the support of an item set. The support is a measure of how often does this set of items happen to appear. So we'll go back to our data and try to measure the support of some items. Imagine that I wanted to measure the support of item number 1, for example. I want to know how frequently do shoppers buy item number 1? Well, in this case, I can see that there's one shopper here, a second shopper here, a third shopper here, and a fourth shopper here. So 4 shoppers out of 5 total have bought item number 1. So something like 80%, for example, have purchased item number 1. But again, we might consider not just individual items, but also sets of items. So sorry, let me just go back. Consider not just individual. So now let's consider how AI might be able to use this kind of technique to be able to look at a whole bunch of data and identify what the frequent item sets actually are. So rather than look at just one shopping basket, we'll look at a whole bunch of different shopping baskets, and we'll look at what items each shopper chose to buy. And so this first shopper, for example, they bought items numbered 1, 2, 3, and 4. I've given each item in this case just a number to identify it. And each of our other shoppers, they've also purchased some items based on the objects that happen to be inside of their cart as well. And so now what we're interested in knowing is we're interested in knowing what the frequent item sets are. We want to know what's popular at this particular grocery store, for example. And so what we're interested in measuring is something that we call the support. The support is a measure of like how frequently does a particular set of items appear in the data set. So if we go back to take a look at our data, we might ask, like, what is the support of item number 1? How frequently do our shoppers buy item number 1? And well, if we take a look, we see that there are 4 shoppers, 1 here, 2, 3, and a 4th shopper over there. 4 shoppers have bought item number 1 out of a total of 5 shoppers in this case. So something like 80% of our shoppers bought item number 1. Item number 1 appears to be pretty popular. Compare that to something that's less popular, something like item number 8. How many shoppers bought item number 8? Well, it looks like it's only this one shopper over here. So if we only have one instance of a shopper buying item number 8, it has a lower support. There are fewer people that are interested in buying item number 8 in this case. But remember that we're interested in not just in the support of individual items, but we're interested in item sets, collections of items that are bought together, and understanding which items tend to be bought alongside each other inside of the grocery store. So we might say, instead of just looking for how popular is item number 1 and how popular is item number 8, I might ask a question like, how popular is it that items 3, 4, and 7 are all bought together? And how often do we see 3, 4, and 7 all bought together? Well, in this case, we see it in these 2 shoppers. And for 2 shoppers, they bought all of these items, 3 and 4 and 7. It's not just that they appear often individually, but they appear often together as a group, in this case, in 2 out of the 5 shoppers. And so that's what we're looking for. We're looking for the frequent item sets. And in this case, we were able to find ones like 3, 4, 7 reasonably easily. It probably wouldn't have been too hard to try and find a set of 3 items that appears at least twice. But again, as the number of shopping baskets increases, as we start dealing with many, many, many more pieces of data across many more individual items, maybe not just the 9 items you see here, but even more than that, it can start to get computationally infeasible for a computer to make its way through all of those efficiently in a really short amount of time. And so ideally, we want better algorithms, better processes that we can use to have AI look at this information and identify the relationships, identify what the frequent item sets are. So we'll introduce an algorithm that'll do just that, and that algorithm is called the a priori algorithm. And so how does the a priori algorithm work? Well, the idea is that we'll go ahead and take all of our items 1, 2, 3, 4, 5, 6, 7, 8, and 9, and then we'll take all of our data. So here then are our individual pieces of data across each of our 5 shoppers. Here are the items that the first shopper bought, the second shopper, the third shopper, 4th, and 5th shoppers. And what we're going to do is start with sets of 1, meaning individual items. and just calculate how frequently do each of those appear. And if we do that calculation across all of them, we decided that item number 1, that was bought by 4 out of our 5 shoppers, so it had 80% of the time it appeared. Item number 2, meanwhile, only appears 1 time, so that's just 20%. And we can do that same calculation across each of these individual items. And then what we want to do is we want to say eliminate the ones that aren't popular, that aren't frequent. And we get to decide what we want to define as the threshold for frequent. But what we might say in this case is, well, if it only appears once out of these 5 shoppers, it's definitely not frequent. So let's make sure it appears at least twice out of the 5 shoppers, meaning at least 40% of the time. In this case, that'll be our definition of frequent. So anything that doesn't appear frequently, which in this case would be things like item number 2 and item 6 and item 8 and item 9, we'll go ahead and eliminate those. Those are not frequent. And what we're left with are the individual items that are frequent by our definition of frequent. Item 1, item 3, item 4, item 5, and item 7. So that then works for individual items. We've identified singular items that are popular. But now, what do we do about looking at pairs of items that are popular, item sets of size 2, 2 items that are frequently bought together? Well, I could take all of my 9 items and consider all of the possible pairings. I can look at 1 and 2 together, and 1 and 3 together, and 1 and 4, and so on and so forth, and then 2 and 3, and then 2 and 4, and so on and so forth. But better yet, I can take advantage of some of the information that I already know. If I know that item number 2 is not popular by itself, well, then there's no way that items 1 and 2 together are going to be popular, because item 2 by itself wasn't frequent. And so what I can do is just take the individual items that are frequent, 1, 3, 4, 5, and 7, and let me make pairs of 2 out of just those items. So I get 1 and 3, and 1 and 4, 1 and 5, 1 and 7, and then 3 and 4, and 3 and 5. Each one of these pairs of 2 items, each one of these sets of 2 items, is made up only of the individual items that I know are themselves frequent. And so I've saved myself some time by not bothering to consider items like 2 and 3 together that I know isn't going to be frequent, or 5 and 6 together that I know won't be frequent as well. So now let me consider just these pairs and go back to the data. Here's that data again. And let's count up how frequently does each pair of items appear. And we can do that math and see that, say, like items number 1 and 3, maybe those show up 60% of the time, because I have one shopper here that bought 1 and 3. I have a shopper here that bought 1 and 3, and a third shopper over here. So 3 out of the 5, that's 60%. And I can do that math for all of the sets of 2. And then again, we apply the same rule. We decided that frequent meant that at least 2 out of our 5 shoppers, or 40% of our shoppers, chose to buy the items in that item set together. So anything that doesn't have at least 40%, we can go ahead and eliminate. So 1 and 7, 3 and 5, 4 and 5, and so forth. We can go ahead and eliminate those from consideration as well. I'll take a pause and then go from 2 to 3. So now, not only have we identified the individual items that are frequent inside of our data set, we've also identified the size 2 item sets that are frequent, the pairs of items that are frequently bought together. And maybe you can see where this algorithm is going, because I can keep increasing the size of the item set and do the same thing. Now I want to consider not just sets of size 2, but I want to consider sets of size 3. And again, I can do that by only combining the sets of size 2 that I know were already popular. So for example, if I know that 1 and 3 are frequent, and I know that 1 and 4 are frequent, I can combine them together, create 1, 3, and 4, make an item set of size 3 that maybe will be frequent, maybe it won't be. We'll be able to tell in just a moment. And so we can start doing that logic, come up with sets of 3. In this case, we know that 1 and 3 are frequent, and 1 and 5 are frequent. So maybe 1, 3, and 5 will be frequent as well. We can combine those and start to come up with some possible candidates of sets of 3 items that we think might be frequent. But in fact, we can do a little bit better than that. I created this list just by combining examples from here that I knew were frequent, but we can eliminate some others right away. For example, I took 1 and 3 and 1 and 5 and combined them to form 1, 3, and 5 as a potential candidate for something that might be a frequently occurring item set. But actually, I can eliminate this one right away, because inside of 1, 3, and 5 is this pair, 3 and 5. And I know from my data already that 3 and 5 is not frequent. 3 and 5 does not appear very often together. So if 3 and 5 on its own doesn't appear very often together, there's no way that 1, 3, and 5 together is going to be frequent either, so I can eliminate that. In fact, I can eliminate many of these on the basis of the fact that they contain within them a set of 2 that isn't already frequent. The only ones I can really consider are 1, 3, and 4, because I know that 1 and 3 are frequent, and 1 and 4 are frequent, and 3 and 4 are frequent, and likewise for 3, 4, and 7 as well. So I'm left with, in this case, just 2 possible candidates for sets of 3 items that I might need to look into. Much more efficient than having to consider all of the possible sets of 3 items that I might need to look into. But we'll go ahead and measure that. And in this case, we'll find that each one of them shows up about 40% of the time. And so at that point, we might say, all right, we've now identified sets of 3 items that tend to be frequent. Maybe we should combine them and see if the set of 4 might be frequent. Combine 1, 3, and 4, and 3, 4, and 7. We get 1, 3, 4, and 7. But already, I think we can probably tell that this isn't going to be a frequent item set, because contained within this set of 4 are 1, 3, and 7, for example. And 1, 3, and 7 is one of those that we already eliminated. We know that's not a frequent set of 3, so there's no way 1, 3, 4, and 7 is going to be a frequent set of 4. And so at that point, we might stop the algorithm. And so what this algorithm has allowed us to do is take all of the data and just very quickly filter down to what do we think is going to be popular, what do we think is going to be frequent, and we can eliminate anything that we know isn't going to be frequent to help make this algorithm a little bit more efficient. And so what do we do with that information? Well, one thing we can now do is try and understand the relationships between those frequent item sets. For example, we knew that the set of 3, 4, and 7 was a frequent item set. Those 3 items tended to be bought together. And so we might ask the question, what is the relationship? How strong is the relationship between items 3 and 4 and item number 7? Meaning, if I know that a shopper bought items 3 and 4, how often are they also buying item number 7? What does that relationship look like? And that relationship is something that we call the confidence of this association. Confidence measures how strong the association is between 2 different sets of items. So in this case, I'm interested in measuring how strong is the relationship between buying 3 and 4 and buying 7. Well, how many of our shoppers bought items 3 and 4? Turns out there are 3 of them. So 1, 2, 3 shoppers bought items 3 and 4 together. And of those 3 shoppers, how many of them also bought item number 7? Well, in this case, just 2 of them. We have a shopper here and a shopper there. Both of them also bought item number 7. So out of my 3 shoppers, 2 out of the 3 bought item number 7 as well. So we might describe the strength of this relationship as like 2/3 or 67% approximately, meaning 67% of the time, if a shopper buys items 3 and 4, they're also going to buy item number 7. And that might be a useful piece of information that we could then use. Meanwhile, if we considered a different relationship, let's look at the relationship between 4 and 7 and item number 3. Well, how often do people buy items 4 and 7? There are 2 cases here where both of these 2 shoppers bought items 4 and 7. And in both cases, buying 4 and 7, those shoppers also bought item number 3. And so 100% of the time, if you bought 4 and 7, you're also buying item number 3. And of course, this is a pretty limited data set. We're only looking at 5 shoppers. But across a much larger data set, you might be able to learn some useful patterns. Understanding something about your customers' behavior. When they do one thing, they tend to do another thing. So that might work in the context of shopping, knowing what items to suggest that you might want to add to your cart. It might work in the context of your smart home or your smartphone, suggesting that we know that when you use this app, you tend to use that app too, understanding the relationships and the association between items inside of a larger data set. OK, I'll take a moment, and then the last section will be recommender systems. So we've now looked at a few different ways that AI can analyze data. AI can look at data and try and understand what the association rules are. AI can take some data and try and cluster it as well. And now we'll look at one other thing AI might be able to do with data, and that is make recommendations to you. We'll talk about the design of recommender systems, which are AI systems that can suggest something to you, recommend something to you that you might like. And maybe you've encountered this in the form of movie streaming websites or video websites that you might use, where an AI might notice what videos and sorry, let me start that over again. We'll just go back. So now we've seen a few different ways that AI can try to analyze data. AI can take some data and try and understand the associations between items in that data, or AI can take data and try and cluster it into different clusters, different groups of related items. And now we'll look at one final type of way that AI might try to analyze data today, and that is in the design of recommender systems. Recommender systems are all about AI taking some information and using that information to try and make recommendations to you, recommendations for things that you might like. And you might have seen this come up in the form of TV and movie streaming websites, where, for example, an AI might pay attention to what movies you choose to watch. And based on the movies you choose to watch, AI might recommend other movies that it thinks that you might like in the future. So it looks at the movies that you've seen before, and it makes some suggestions to you, some recommendations to you on what it thinks that you're going to like. And so how might that work? How might we have a whole bunch of movies, for example. How might AI make a prediction as to, I think this is a movie that you're going to like? Well, it's got to use data somehow, information about the movie or information about you, to be able to use that information to draw some kind of conclusion, to be able to suggest to you some kind of movie that you might enjoy. And so what might that look like? Well, every movie has a whole bunch of properties, a whole bunch of features to it, for example, that we might describe that might be useful in trying to produce a recommendation. Movies have a particular genre. Movies were made in a particular year. Movies have a particular director. And all of that might be useful for informing recommendations. For example, if AI learns that you really like movies that are by a particular director, or if it learns that you really like movies with a particular actor in it, or that were made in a particular genre, for instance, all of that can be information that AI uses to try and make some good predictions as well. And so what could we do? We could try and apply a nearest neighbor type of classification system to this. So we saw last time, let me, what's a good way to go back to this? I realized I misspoke because I said last time, but it was actually 2 chapters ago that we talked about nearest neighbor, so I want to avoid that. Or actually, no, it was last time. I was right. Second guess myself. Let's see. I guess I'll just go back from the beginning of this slide. So every movie has a number of different data points or different features that we might use to inform some recommendation. Every movie has a genre, a year that that movie was released, a director, the actors that appeared in that movie, for example. And AI might use that information to make some judgments about what kind of movies it thinks you might like. That if it learns that you really like movies by a particular director, or that have particular actors in it, or that are of a particular genre, well, then AI might learn that it can recommend more things like that to you in the future. So what could we do with that? Well, we could take an approach that we've seen before. Before, when we were talking about classification, we learned about nearest neighbor classification, where the idea of nearest neighbor classification was that in order to classify something into one category or another, we looked at some training data, we looked at which item in that training data some new point was nearest to, and used that to make a decision. And you might imagine we could use a nearest neighbor type of classification system for trying to make movie recommendations to you as well. For example, if AI knows that you liked a particular movie, maybe because you watched the whole thing, or maybe because you wrote a review or gave it a thumbs up rating at the end, then it knows that you liked this particular movie with all of the features and data points that are part of that movie. And maybe it also knows about a movie that you didn't like. And how would it know that you didn't like that movie? Well, maybe you didn't finish the entire movie, or maybe you watched the movie but you gave it a thumbs down rating at the end. All of those are possible ways that a computer might know what kinds of things you do or don't like. But then if a new movie comes along, and it's very similar in spirit to a movie that it knows that you did like, because it has a similar director, maybe it's of a similar genre, maybe it's got similar actors, maybe it was produced at a similar year, maybe it's got a number of these features that are all similar to a movie that you like, well, that might increase the likelihood that AI recommends that to you because it's similar to content that you have already enjoyed. And this approach to trying to make recommendations is something that we call content-based filtering. We're filtering down the space of possible movies in this case based on their content, based on things we know about that movie, and trying to say, if I know you liked these movies and I know you didn't like those movies, well, then if I'm looking at some new movie, I'll compare it and basically say, what features does it have? Does it have the kinds of things you tend to like in a movie, or does it tend to have the things that you tend to not like in a movie? And use that to try to make some helpful recommendations to you as well. And so how could this work? How could you use like a nearest neighbor-like approach or some other similar type of algorithm to do content-based filtering? Well, remember that computers are really good at dealing with numbers. That ultimately, if we can take data and turn it into numbers, then a computer is going to be able to work with it and be able to compare those numbers, figure out which ones are closer together or further apart. And some of the features we talked about are already numbers, like the year that a movie was published in, how long it is, its duration in minutes, for example, maybe its budget in millions of dollars, for instance. All of those are numbers, data points that we could use in order to do a comparison. So that if AI learns, you really don't like long movies and you like movies that are a little bit shorter, that's something it could learn by comparing the duration of movies you did like and durations of movies you didn't like, and then use that to try and inform some additional recommendations. But there are also some data points that don't translate directly into a number. For example, genre, that's not a number. If we could say that there are action movies and there are comedy movies and there are drama movies as well. And so these are not numbers. And so how do you compare distances in that sense? How do you find the nearest neighbor in that sense? Well, we have a few different options. One option would be, we'll take every genre, action and comedy and drama and romance, and we'll turn them into a number. So that action movies, all action movies, they will have a genre of 1. And all drama movies, they'll have a genre of 2. And comedies will be 3. And romance will be 4, for example. And we could do that. But again, that introduces a problem we've talked a little bit about before, which is it implies some kind of ordering between the different genres, that genres 3 and 4 are closer together than genres 2 and 4. And that might be true, but at the time that we're trying to make this decision, we might not know that for sure. And so often, rather than just use like a single variable, a single number to represent the genre, we might split it up into multiple different numbers to try and represent it. We might give a number for action. Is it an action movie, yes or no? Is it a comedy movie, yes or no? Or instead of yes or no, 1 or 0. So if it is an action movie, for example, then the value for action will be a 1. And for all of the others, it'll be a 0, for example. And that allows me to do things like, say, make sure that every genre is independent. Each genre is separate from each other, and we're not in danger of trying to confuse those potentially. OK, I'll pick up from there in a moment. And one other advantage of representing data like this is it gives us the capacity to represent movies that might fall into multiple different genres at the same time, something that we couldn't do when we were representing a genre with just a single number. If, for example, we have a movie that is an action movie and also a sci-fi movie, well, then maybe we could set the action value to 1 and the sci-fi value to 1 as well. So splitting things up like this, having this distributed representation, has some advantages when it comes towards giving it to the AI and using it to be able to compare across all of these various different features. So that's helpful for things like the year where we already had it as a number, or the duration where it was already the number, and then a genre, which we could turn into a number. But how do we then deal with problems like text, where we might imagine that maybe we use a description of a movie, and we want to use that description of the movie to be able to identify useful information too. Like ideally, if we can use the words in this description and say, if you liked this movie, then maybe you'll like another movie that has a description that has similar words inside of it too. Well, we'll run into some problems here if we just try and pay attention to all of the words that happen to show up in this description, because a bunch of the words are probably going to show up in a lot of different movie descriptions. Like I wouldn't want to say, oh, if you liked this movie, and I look at this description and I see, OK, the word the is in here. Well, then maybe if the word the appears in another movie description, I don't want to say you might like that movie, because to be honest, the word the is probably going to appear in a lot of different movie descriptions. But there are some keywords, at least in this particular description, that my eyes might catch on to. For example, the word magical. The word magical appears twice. That maybe suggests that this movie has something to do with magical things that might be happening. And so maybe if you liked this movie, you might also enjoy other movies in which magical things are happening. Whereas I would want to pay attention to that, but I probably wouldn't want to pay attention to the fact that like the word she appears 3 times, because the word she probably appears in lots of movies. It might not be that strong of an indication of how much we think you're going to like this particular or that particular movie in general. And so those are some of the ideas we're dealing with. And so what we're interested in knowing is what strategies can we use to try and figure out what the important keywords are inside of something like a movie description. And it's not quite as simple as just saying, what are the frequent words? Because the word magical appears twice, but the word she appears 3 times. But I would argue that the word magical is probably more special to this particular description. It's going to be rare that that keyword shows up, so that's going to be a keyword I want to pay more attention to. And so the formula I could use in this case is, rather than just consider how frequently does the word appear in a document, the document in this case being the description of the movie, what I can do instead is take the frequency of the word in the document and divide it by the frequency of the word across all of the documents, across all of the different movie descriptions that I might have. So if a word appears frequently in a movie description, that increases its importance. That makes it more likely it'll be an important keyword. But meanwhile, if it's a word that appears really frequently across a lot of different movie descriptions, well, then this denominator, the thing I'm dividing by, is going to get pretty big too. And so overall, this number, this score, is going to be a little bit less. And so that'll help me focus my attention on the words in that movie description that really matter. So those are some strategies we can then use for this kind of content-based filtering, where I know what movies you like, I know what movies you don't like, and I use that information to try and inform what new movie you might like as well. But another strategy we can use is something called collaborative filtering. And collaborative filtering is about the idea of using information about other users and the types of things that they happen to like too. So let's give an example. Let's imagine that there are 5 movies. And let's imagine that you've watched 2 of these 5 movies, and you seem to like them. You watched this first movie, and you liked this third movie. Now, how do we know what movie to suggest to you? Well, one way we could do that is by looking at other people and looking at what movies they watched and what movies they liked. Maybe if we have another person and they watched these 3 movies here in the middle, and we have another person who watched this first movie and this third movie and that 5th movie, then if I'm trying to recommend a movie to you based on the movies that you've watched, and I know what movies other people have watched and liked, well, maybe I'm going to recommend this 5th movie to you as well, because I know that this person down at the bottom here, they watched similar movies to you, they liked similar movies to you, and based on that information, another movie that they liked might be a movie that you would like as well. And so what might that look like? Well, if we had a bunch of data across a bunch of different people and movies that they liked and how they chose to rate a particular movie, maybe all these people watched the movie and we can make a judgment as to how much they liked it and how much they didn't like it based on how much of the movie they watched, or based on whether they gave it a thumbs up or thumbs down review at the end of it. Well, then if we're wondering if you, some new person, are going to like that particular movie, we can look at who are the people that are close to you, who are the people that have similar tastes to you, that have watched similar things to you in the past, and then say, do those people like this movie that you might be interested in? And if so, maybe it's one we recommend to you, and if not, maybe it's one we don't recommend to you. But using data from other people can be a helpful tool for trying to figure out what you might like and what you might not like in the future. And how good is this kind of approach? Well, ultimately, it comes down to how much data you have. That as you have more and more data across more and more people, more and more different movies that they've seen and not seen, liked and disliked, we can use all of that information, use much more data to be able to come up with much more accurate predictions for what kind of movie you might like and what movie you might not like, because we have more information to compare you against, more different people, more movies in our database that we can use to try and make those kinds of judgments. And that's one of the reasons why many companies nowadays are increasingly interested in getting access to and collecting more and more user data, because they can use that data to try and make useful predictions as well. And that's something for, sorry, one moment, and then we'll wrap this up. So that's one of the reasons why companies are increasingly interested in collecting more and more data, because the more data they have about more users and more movies in this case, the better recommendations they can make, the more likely they can suggest to you a movie or a TV show that you'll end up watching, so you'll spend more time on that platform. And so in some sense, that might be good for you. Maybe the more data the company has, it can recommend to you something that you might enjoy, but also be aware that you are benefiting from the information around you and the information that is being collected about other users. But at the same time, information is being collected about you too. The information about what you watched and what you like might be used to inform recommendations and predictions given to other people too. And you might be OK with that, or you might have reservations about that. But it's important to be mindful and to know that when you're interacting with services, especially on the internet nowadays, knowing what data is being collected about you, what that data is being used for. And if you want to, many websites will give you the option to opt out, to decide that you don't want your data to be used as part of this training set, to be used in order to monitor your activity and make recommendations for others as well. And so if you're concerned about those types of things, that's one thing to be on the lookout for, that oftentimes you have that opportunity to opt out of data collection in that sense. But again, the more data that is able to be collected, that often leads to more accurate predictions as a result. And so there's often an incentive to try and collect more and more data about you and about other people as well, to try and inform the kinds of analyses that AI can make. Because ultimately, we've seen many instances now where AI can use large collections of data to be able to make useful conclusions, to be able to cluster data in different formats, to be able to understand relationships between user and shopper behavior in the grocery store, for example, or to be able to make good recommendations for books or movies or TV shows that you might like. And these are all examples of AI being applied to take a whole bunch of data and use that to solve some interesting problems, to be able to do useful things for all of us. So that was today's look at using AI to analyze data. And next time, we'll continue this exploration, looking at other kinds of data that AI can use too, not just numbers, but information like visual and auditory information we get from our senses, to think about how AI might be able to take advantage of that information too, to be able to make useful conclusions, draw useful predictions, and ultimately make better use of an increasingly wide variety of data as well. So we'll see you next time. Thanks, everyone.